Now, challenge problem 1 says find the intervals on which the function f is increasing or decreasing, concave up, concave down, and the location of any relative extrema, inflection points, asymptotes, and intercepts. Use a graphing utility to verify your results. So basically, we're putting everything together in this one particular example. So let's go ahead and do it. First thing we're going to figure out are the intervals on which the function is increasing or decreasing. To do that, we need to figure out what the critical numbers are. Remember, critical numbers occur wherever the first derivative is either equal to 0 or does not exist. So we need to figure out the first derivative of this function. So let's take the derivative of this function. To take the derivative of this function, this is pretty easy. You just take the derivative of each term separately. Derivative of x cubed by the power rule is going to be 3x squared. Derivative of 2x squared, the 2 stays out front by the constant multiple rule, and derivative of x squared, just use the power rule, so it becomes 2x to the first. Then you multiply the 2's together, you get 4x to the first. Over here, this negative 5x, remember the negative 5 stays out front, just take the derivative of x, that becomes 1. So 1 times negative 5 gives you that negative 5, and derivative of negative 6, anytime you take the derivative of a constant, it just becomes 0. So we have our first derivative. Again, critical numbers. Those occur wherever the first derivative either equals 0 or does not exist. Are there any x values that would cause this first derivative to not exist? No, there's no denominator, so we're good. So all we have to do is figure out what values of x would cause the first derivative to equal 0. So we set this equal to 0 and we solve for x. How do we solve this for x? Well, there's a couple different ways to solve for x. One would be to factor this, right? Use a magic x, however you normally do it. But in this particular instance, there's no way to factor this neatly. So what we have to do instead is use the quadratic formula. So remember the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. In this particular instance, 3 is our a, 4 is our b, and negative 5 is going to be our c. So we plug those into the quadratic formula and we simplify. 4 squared is 16, negative 4 times 3 times negative 5 is positive 60. We add those together, we get rad 76. Now we can simplify that and it becomes 2 rad 19. I can then factor out a 2 from each term in the numerator and cancel that 2 out with the 6 in the denominator, making this a 3. So it becomes negative 2 plus or minus rad 19 over 3. These would be the two x values that cause our derivative to equal 0. Now, to make this a little bit easier when I'm filling out my sign chart and picking test x values, I'm going to plug this into my calculator. Negative 2 plus rad 19 over 3 and negative 2 minus rad 19 over 3. I end up getting approximate x values where this derivative equals 0 at 0.786 and negative 2.120. Now again, these are the exact values, these are the approximate values. We're going to use the approximate values in our sign chart over here because when it comes time to picking test x values on given intervals, it's much easier to determine what the interval actually is if it's not something like this. So we are going to create our interval. This function has no domain restriction, so it's going to go from negative infinity to positive infinity. So we start at negative infinity and we go to our first critical number, which is going to be at negative 2.120. Then at x is equal to negative 2.120, we determine whether there's a relative max or min. Then from negative 2.120, we go to our second critical number at 0.786. Then at x is equal to 0.786, we determine whether there's a relative max or min. Lastly, we go from 0.786 to infinity. Now, we pick test x values on each of these intervals, plug them into our first derivative to determine whether the function's increasing or decreasing on those intervals. So let's pick a test x value on this given interval. How about negative 3? If I plug in negative 3 to our first derivative and I simplify, I end up getting positive 10. Again, we don't care about the 10, we care that it's positive. Because it's positive, that means the derivative of this function on this given interval is positive, meaning the slopes of the tangent lines to the curve of this function on this given interval are positive, meaning that this function on this given interval is increasing. Now, to figure out whether there's a relative max or min here, we have to figure out what's going on here. Is it increasing or decreasing on this interval? If it goes from increasing to decreasing, there's going to be a relative max. If it goes from increasing to increasing, there's neither a relative max nor a relative min. So here, I pick a test x value on this interval. How about 0? So I plug in 0 to this first derivative and I simplify. I end up getting negative 5. We don't care about the 5, we care that it's negative because it's negative. That means the derivative of this function on this given interval is negative, meaning the slopes of the tangent lines to the curve of this function on this given interval are negative, meaning that this function on this given interval is decreasing. Now we know that our function goes from increasing to decreasing at x is equal to negative 2.120 or negative 2 minus rad 19 over 3. Because of that, we know that there must be a relative max here by the first derivative test. Now we're going to do the same thing here. We pick a test x value on this interval to plug in. How about 2? If I plug in 2 to this first derivative and I simplify, I end up getting positive 15. We don't care about the 15, we care that it's positive. Because it's positive, that means the derivative of this function on this given interval is positive, meaning the slopes of the tangent lines to the curve of this function on this given interval are positive, meaning that this function on this given interval is increasing. Now, because we know that the function goes from decreasing to increasing at x is equal to 0.786, we know by the first derivative test there must be a relative min at this particular x value. Next, we need to determine the intervals on which the function is concave up or down. In order to do this, we need to figure out where the possible inflection points are. Remember, possible inflection points occur wherever the second derivative either equals 0 or does not exist. So we need to figure out what the second derivative is. How do we find the second derivative? We take the derivative of the first derivative. So to take the derivative of the first derivative, we take the derivative of each term separately. The derivative of 3x squared, the 3 stays out front. Just take the derivative of x squared using the power rule, so it becomes 2x to the first. Multiply the 2 and the 3, you get 6x to the first. Over here, taking the derivative of 4x, the 4 stays out front. Taking the derivative of x, that becomes 1. 1 times 4 is 4. Derivative of negative 5, that's a constant, so the derivative of a constant is just 0. Now that we have our second derivative, we can find our possible points of inflection. Remember, those occur wherever the second derivative either equals 0 or does not exist. So, are there any x values that would cause this to not exist? No. So we just have to set it equal to 0 and solve for x. So let's subtract 4 from both sides, divide both sides by 6, and then simplify. We get a possible inflection point at x is equal to negative 2 over 3. Now, why is this important? Because we have to make a sign chart for our second derivative, and we're going to break up the intervals based on whatever our possible points of inflection are. So here we only have one possible point of inflection at negative 2/3. Again, there's no domain restrictions, so our intervals are going to go from negative infinity to positive infinity. And we're only going to break up at our one possible point of inflection at x is equal to negative 2/3. So our first interval is from negative infinity to negative 2/3. Then at x is equal to negative 2/3, we have to determine if there's an inflection point there. And then we go from negative 2/3 to positive infinity. Now we're going to pick test x values on these given intervals to plug into our second derivative and then determine if we get a positive or negative number out. If we get a positive number, we know it's concave up. If we get a negative number, we know it's concave down. So what's an x value on this interval that we can plug into our second derivative? How about negative 1? If I plug in negative 1 to our second derivative and simplify, I end up getting negative 2. Again, we don't care about the 2, we care that it's negative. Because it's negative, that means the second derivative of this function on this given interval is negative, meaning that f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Now we're going to pick a test x value on this interval to plug into our second derivative. How about 0? If I plug in 0 to our second derivative and I simplify, I end up getting positive 4. Again, we don't care about the 4, we care that it's positive. Because it's positive, we know that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. And because your graph goes from concave downward to concave upward at x is equal to negative 2/3, you know that there must be an inflection point at x is equal to negative 2/3. So we figured out the intervals on which the function is increasing or decreasing, concave up or down, and we've determined any relative extrema and inflection points. We now need to figure out the asymptotes and the intercepts. So vertical and horizontal asymptotes require either a trig function or a rational function. Here we don't have either of those. Because there's no numerator or denominator here, we can't have a vertical or horizontal asymptote. So we say there is no vertical asymptote, there is no horizontal asymptote here. Now for the intercepts, let's start with the x-intercepts. To find x-intercepts, I plug in 0 for y and solve for x. Now how do we do that? Well, there's a couple different ways to solve something like this. First would be to graph it. If you have access to a graphing calculator, obviously that would be the best because you can determine the x values at which the graph crosses through the x-axis. Those would be your solutions. If you don't have access to a graphing calculator, you may need to factor this. Now, there are several different ways to factor a polynomial. One such way would be factor by grouping, but this particular polynomial does not factor by the factor by grouping method. So we need to use something called the rational root theorem. Now, if you recall, the rational root theorem says all possible roots of a particular polynomial can be found using the positive or negative version of the factors of your last term of your polynomial over the factors of your leading coefficient. So what are the factors of 6? That would be 1, 2, 3, and 6. What are the factors of 1? That's just 1. So you would have 1 over 1, 2 over 1, 3 over 1, and 6 over 1. Negative 1 over 1, negative 2 over 1, negative 3 over 1, and negative 6 over 1. Those are all the possible roots of this particular polynomial. So how do you determine if it's a root? Well, you can use synthetic division and determine if that potential root divides in evenly to this polynomial. So let's try 2. 2 is one of our potential roots. So I'm going to use synthetic division. I'm going to put 2 here. Over here, I'm going to put the coefficients of each of these terms. So it's going to be 1, 2, negative 5, and negative 6. Now, if you recall, synthetic division works like this. I'm going to take this 1, move it down here. I'm then going to multiply these two numbers. 2 times 1 is 2, and I put that here. I then add down. 2 plus 2 gives me 4. That goes here. Then I multiply again. 2 times 4 gives me 8. That goes here. Then I add down. 8 plus negative 5 is 3. Then I multiply. 2 times 3 is 6. I then add down, and I get 0. So this in here is my remainder. Because my remainder is 0, that means that 2 goes in evenly, meaning that 2 is going to be one of my roots of this polynomial. Now, how does that help? Well, if 2 is a root of this, that means x minus 2 has to be a factor of this polynomial. So it looks something like this. This is how you use synthetic division. Because 2 is a factor, it divides in evenly to this polynomial with synthetic division. I then write the factored form as x minus 2, because if x minus 2 is a factor, that means 2 is my root, because 2 would cause this to equal 0. Over here, I then write what I get when I use synthetic division. Remember, I have to start with 1 degree less than what I started with up here. So that's why it's 1x squared plus 4x plus 3. Now, this is this polynomial factored, but not completely factored. Here, x squared plus 4x plus 3, this is a quadratic trinomial, which I can factor more. So this actually is going to factor into x plus 3 times x plus 1. Now, this right here is the completely factored form of our given polynomial. Now what I can do is use the zero product property and say, if this times this equals 0, then either this equals 0, this equals 0, or this equals 0. And I can solve each of these for x by adding 2 on both sides, subtracting 1 on both sides, subtracting 3 on both sides. And I have found my 3 roots for this particular function. Now remember, roots are the same as x-intercepts, which are the same as zeros. So to write these as points, this is going to be the point 2, 0. This is going to be the point negative 1, 0. This is going to be the point negative 3, 0. Those are going to be my x-intercepts. Now to find my y-intercepts, I'm going to plug in 0 for x this time and solve for y. So if I plug in 0 for x and simplify, I end up getting f of x, or y, is equal to negative 6, which means this function has a y-intercept at 0, negative 6. Now let's confirm all of this with our graphing calculator. We start by remembering our sign charts from before. Our function is going to be increasing from negative infinity to negative 2.120, which you see it is, and it's also concave down on that given interval. Then we see at x is equal to negative 3, we do have an x-intercept. Perfect. At x is equal to negative 2.120, we can also see that we have a relative maximum, just like we confirmed. Then our function starts decreasing on the interval from negative 2.120 to 0.786. We see at x is equal to negative 1, we again have an x-intercept. Perfect. And at x is equal to negative 2/3, we have our inflection point. We then see that the graph changes from decreasing and concave down to still decreasing but concave up now. And you can see that at x is equal to 0.786, we do have a relative minimum, like we said. And then after that, from 0.786 to infinity, our graph is concave up and increasing. And we see that at x is equal to 2, we again have our last x-intercept. Lastly, we see that our y-intercept was at 0, negative 6. Boom, done. Okay, challenge problem 2. We're doing all the same stuff, except this time we got some trig in here. First thing we're going to figure out are the intervals on which the function is increasing or decreasing. To do that, we got to figure out what the critical numbers are. Remember, critical numbers occur wherever the derivative of your function is either equal to 0 or does not exist. So we need to figure out what the derivative of this function is. To take the derivative of a function divided by another function, or to take the derivative of a quotient, you need to use the quotient rule. Quotient rule says you take the derivative of the numerator, multiply it to the denominator. denominator. Then subtract the numerator times the derivative of the denominator all over the denominator squared. Now we're going to take the derivative of each of these terms here. Derivative of cosine of x is just going to be negative sine of x. Derivative of 1 plus sine of x, you take the derivative of 1, which is 0, and then the derivative of sine of x, which is cosine of x. Now I'm going to distribute this negative sine x to the 1 and to the sine x over here. I'm then going to multiply these two cosines together, and I get cosine squared x. Now what I can do is up here in the numerator, it looks like there's nothing else I can simplify, but if I factor out a negative 1 from each of these three terms, I get negative 1 times the quantity sine x plus sine squared x plus cosine squared x. Now you should remember one of your trig identities, probably the most famous one, is sine squared x plus cosine squared x is equal to 1. So I can substitute in a 1 for sine squared x plus cosine squared x. Now why do I do that? Because I now have a sine x plus 1, or I could rewrite that as 1 plus sine x in the numerator, as well as two of them in the denominator. So this is going to cancel out with one of these in the denominator, and I end up getting my derivative, which is negative 1 over 1 plus sine of x. Now why did we just find the derivative? Because we're trying to find the critical numbers. And critical numbers, we said, occur wherever the first derivative is either equal to 0 or does not exist. So we need to set this equal to 0 and solve for x. In order for a rational function like this to be equal to 0, just the numerator has to be equal to 0. So what can I plug in for x up here? Oh, there is no x up here. So there is no x value that would cause this to equal 0. But are there any x values that would cause this to not exist? In other words, what values of x would cause our denominator to equal 0? So you set the denominator equal to 0 and solve for x. You subtract 1 on both sides. You get sine of x is equal to negative 1. You could take the inverse sine of both sides, or you could just know your unit circle. And since our domain is restricted from negative pi to 2 pi, we think about on that interval, what x values would cause sine to equal negative 1. And that would be negative pi over 2 and 3 pi over 2. Now, the issue with these two numbers is that if we look up here, 1 plus sine x is also in your denominator of your original function. And if an x value causes the denominator of your original function to equal 0, that means that's where a vertical asymptote is going to be. So there's going to be a vertical asymptote at x is equal to negative pi over 2 and 3 pi over 2. So now we make our sign chart, and we break up our sign chart based on these critical numbers. Again, our domain is restricted, so we're not going from negative infinity to infinity this time. We're starting at negative pi, and then we're going to our first critical number, which is negative pi over 2. And then at x is equal to negative pi over 2, we got to figure out what happens in the graph. Well, we already know it's vertical asymptote. Then we're going to go from negative pi over 2 to our next critical number, which is 3 pi over 2. And then at x is equal to 3 pi over 2, we got to figure out what happens in our graph. Again, we know it's a vertical asymptote. And then we go from 3 pi over 2 to the end of our interval, which is 2 pi. Now, we're going to pick test x values on each of these intervals to plug into our first derivative down here, and then see what the sign is of the number that we get out. If we get a positive number, that means the function is going to be increasing on that given interval. If we get a negative number, the function is going to be decreasing. So let's pick a test x value on this given interval. How about negative 2 pi over 3? If I plug in negative 2 pi over 3 for x in our first derivative down here, and I simplify, I end up getting negative 1 over 1 minus rad 3 over 2. Now, why didn't I just plug this in my calculator? Because a lot of times you will be given these types of questions on the non-calculator portion of the AP test. So you need to be able to simplify this in your head and just determine, is it going to give you a positive or negative number? You don't even have to get the exact answer. Just, is it going to be positive or negative? Well, the numerator is negative 1. The denominator is 1 minus rad 3 over 2. Rad 3 over 2 is less than 1. Therefore, my denominator is going to be positive and my numerator is going to be negative. So I'm going to get a negative number, meaning the derivative of this function on this given interval is negative, meaning the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval is decreasing. We already said that at x is equal to negative pi over 2, we have a vertical asymptote, because if I were to plug in negative pi over 2 for x in my original function, it would cause my denominator to equal 0. Now let's pick a test x value on this given interval. How about 0? If I plug in 0 to the first derivative and I simplify, I end up getting negative 1. Again, we don't care about the 1, we care that it's negative. Because it's negative, that means the derivative of this function on this given interval is negative, meaning the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval is decreasing. At x is equal to 3 pi over 2, we have another vertical asymptote, because if I were to plug in 3 pi over 2 for x in my original function, it would cause my denominator to equal 0. Now let's pick a test x value on this given interval. How about 5 pi over 3? If I plug in 5 pi over 3 for x in the first derivative and I simplify, I end up getting -1 over 1 minus rad 3 over 2 again. We said that the numerator is negative and the denominator is positive. Because we have a negative number over a positive number, we know it must be negative, which means the derivative of this function on this given interval is negative, meaning the slopes of the lines tangent to this function on this given interval are negative, meaning that this function on this given interval must be decreasing. So the function is decreasing throughout the given interval. Interesting. Now let's figure out where the graph is concave up or down. So to determine concavity, we need to figure out the possible points of inflection. And possible points of inflection occur wherever the second derivative is either equal to 0 or does not exist. So we need to take the derivative of our derivative. So how do I take the derivative here? Well, there's a couple different ways. Because it's written as a rational function, you could technically use the quotient rule to take the derivative of this. But there is no x in the numerator. So to make it easier on yourself, what you could do is take this denominator, move it to the numerator, and give it a negative exponent. Now we see that it's much easier to take the derivative of because all I have to do is use the constant multiple rule, take this -1, move it out front of the derivative sign. So all I'm doing is taking the derivative of 1 plus sine of x to the negative first power. And that requires the chain rule. The chain rule says I take the derivative of my outermost function first, which is this something raised to the negative first power. So I'm going to take the derivative of that by bringing the -1 out front, 1 plus sine x, that in here stays the same. Then I subtract 1 from this exponent, so it becomes the negative second power. And then I multiply by the derivative of my inner function. The derivative of my inner function is going to be 0 plus, and the derivative of sine is just cosine. So that's how I get this. Now this -1 times -1, those become a +1. This 1 plus sine of x to the negative second, I can bring down to the denominator, and I have my second derivative. Now why did I find the second derivative? Because I'm trying to figure out possible points of inflection. And those occur wherever the second derivative is either equal to 0 or does not exist. So I'm going to set this equal to 0 and solve for x. Now remember, because it's a rational function, in order for this to equal 0, we just need the numerator to equal 0. So we look at our unit circle and we determine what values of x would cause cosine to equal 0. Well, that would be -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on in both directions. But we know the domain is restricted on this given interval, so that would just be these 3 values. We also know that for this particular function, at x is equal to negative pi over 2 and x is equal to 3 pi over 2, we have vertical asymptotes. So those cannot be points of inflection because they're vertical asymptotes. So the only possible point of inflection left would be pi over 2. So we need to check that out. Now we're going to create our sign chart for the second derivative to determine concavity. Remember, our domain is restricted from negative pi to 2 pi. So when we're creating our intervals, we need to keep that in mind. We start with the beginning of our domain restriction, which would be negative pi. And we go to our first vertical asymptote, which is at negative pi over 2. We then, at x is equal to negative pi over 2, have to determine what's happening. We already know it's a vertical asymptote. Then we go from negative pi over 2 to pi over 2, our possible point of inflection. And then at x is equal to pi over 2, we have to determine what's happening in the graph, whether it's going to be an inflection point or not. Then we go from pi over 2 to our second vertical asymptote, which is going to be at 3 pi over 2. And then at x is equal to 3 pi over 2, we have to determine what's happening in the graph. Hint, we already know it's a vertical asymptote. And then we go from 3 pi over 2 to the end of our interval at 2 pi. So now we have to plug in test x values on these given intervals to our second derivative up here and then determine whether we get a positive or negative number out. If we get a positive number, that means the graph is concave upward on that given interval. If we get a negative number, that means the graph is concave downward on that given interval. So let's plug in a test x value on this given interval to our second derivative. How about -2 pi over 3? When I plug that in and simplify, I end up getting -1/2 over 1 minus rad 3 over 2, the quantity squared. Again, the denominator is squared, so that's always going to be positive. The numerator is negative, though, so we have a negative over a positive, which is going to be negative, which means the second derivative of this function on this given interval is negative, meaning f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. Then we know at x is equal to negative pi over 2, we have a vertical asymptote. Now, why did we have to include the vertical asymptote in here? Because your graph could change concavity on either side of the vertical asymptote. So let's check here. Did it change concavity? We plug in a test x value on this given interval. How about 0? We plug that into our second derivative. We simplify. We end up getting +1. Again, we don't care about the 1. We care that it's positive. Because it's positive, that means that the second derivative of this function on this given interval is positive, meaning that f prime of this function on this given interval is increasing, meaning that this function on this given interval is concave upward. So it did change concavity on either side of the vertical asymptote. That's why you have to include that in your sign chart down here. Now, at x is equal to pi over 2, what's happening? Well, we don't know. Remember, this is a possible point of inflection. So if our graph goes from concave upward to concave downward, we know there's an inflection point here. But if it goes from concave upward to concave upward, then we know that this is not going to be an inflection point. So let's determine what's happening over here. We plug in a test x value on this given interval to our second derivative. We're plugging in pi. We simplify. We end up getting -1. Again, we don't care about the 1. We care that it's negative. Because it's negative, that means the second derivative of this function on this given interval is negative, meaning that f prime of this function on this given interval is decreasing, meaning that this function on this given interval is concave downward. And now we know that the graph is going from concave upward to concave downward at x is equal to pi over 2. Therefore, there must be an inflection point at pi over 2. Now, what's happening at x is equal to 3 pi over 2? Oh, we already know. It's vertical asymptote, so we can just plug that in there. And now we have to determine what's going on over here. So we pick a test x value on this given interval, plug it into our second derivative. We plugged in 5 pi over 3. We're going to simplify. We end up getting positive 1/2 over 1 minus rad 3 over 2, the quantity squared. Again, denominator squared, so that's always going to be positive. Up here, our numerator we know is positive. Therefore, we know that this must be positive. Because it's positive, that means the second derivative of this function on this given interval is positive, meaning f prime of this function on this given interval is increasing, meaning this function on this given interval is concave upward. Now that we've figured out where the function is increasing or decreasing, concave up, concave down, the location of any relative extrema, and inflection points, we need to figure out the asymptotes, the intercepts, as well as its period this time. So let's start with the period. In the previous slide, we saw that asymptotes occur at negative pi over 2 and 3 pi over 2, but they continue on in both directions. And what is the space between negative pi over 2 and 3 pi over 2? Well, that would be 2 pi. Therefore, the period of this function is going to be 2 pi. That's how long it takes for the function to repeat. Now we can talk about asymptotes. So for vertical asymptotes, we already know that on this given interval, this function has vertical asymptotes at x is equal to negative pi over 2 and 3 pi over 2, because those would cause the denominator to equal 0. Now let's talk about horizontal asymptotes. So normally when we're talking about horizontal asymptotes, we're looking at the degree in the numerator over the degree in the denominator. If the degree in the denominator is greater than the degree in the numerator, there's a horizontal asymptote at y equals 0. If the degrees are the same, then we look at the ratio of the leading coefficients. If the degree in the numerator is greater, then we know that there is no horizontal asymptote. In this particular instance, there is no x squared. There's no x cubed. We have to look at the limit as x approaches infinity. If you look at the limit as x approaches infinity of cosine, that oscillates back and forth between 1 and -1. If you look at the limit as x approaches infinity of 1 plus sine of x, this is going to oscillate back and forth between 1 and -1. So this denominator will just oscillate back and forth between 0 and 2. Now, because the numerator and denominator are both oscillating like that, the limit as x approaches infinity of this function diverges. So there would be no horizontal asymptote here. Now, x-intercepts. To determine x-intercepts, you're going to plug in 0 for y and solve for x. So we need to plug in 0 for f of x over here and solve for x. Now again, the only x values that would cause this rational function to equal 0 would be x values that cause the numerator to equal 0. And we already determined this. What values of x cause cosine to equal 0? Well, that would be negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and so on. What about on this particular interval? Well, on this given interval, we know it's going to be negative pi over 2, pi over 2, and 3 pi over 2. And we already said that at x is equal to negative pi over 2 and at x is equal to 3 pi over 2, this function has vertical asymptotes. So the only x value here at which this function is going to have an x-intercept is at pi over 2. So we know the x-intercept of this function on this given interval is going to be at pi over 2 comma 0. Now what about the y-intercepts? To figure out y-intercepts, you plug in 0 for x and you solve for y. So we plug in 0 for x here. Cosine of 0 we know is 1. Sine of 0 we know is 0. So we end up getting 1 over 1, which is 1. Meaning that this function on this given interval is going to have a y-intercept at 0 comma 1. Now we can confirm all of this with our graphing calculator. Let's take a look. We can see from negative pi to negative pi over 2, the function is both decreasing and concave down, just like we said. Then at x is equal to negative pi over 2, we have the first of our vertical asymptotes. Then from negative pi over 2 to pi over 2, we see that the function is both decreasing and concave upward. Then at x is equal to pi over 2, we have our x-intercept. We also have our inflection point. That means that the graph is going to change from concave upward to concave downward, which it does. So you see that from pi over 2 to 3 pi over 2, the function is both decreasing and concave downward, just like we said. Then at x is equal to 3 pi over 2, we have the second of our vertical asymptotes. Then after that, from 3 pi over 2 to 2 pi, the function is both decreasing and concave upward, just like we said.